In section 3.6, we're talking about theorems concerning perpendicular lines. Everything will be about perpendicular lines today, looking at some more theorems and some proof to go along with it. First two theorems. If two lines intersect to form a linear pair of congruent angles, then the lines are what? Alright, let's draw a picture. Two lines are intersecting. They form a linear pair. Remember, a linear pair is a pair of angles on a line. So they form a pair of angles on a line. So I'll put my line. Okay, two lines are intersecting. So I have another line intersecting it. And it's forming this linear pair, pair of angles on a line, of congruent angles. So these two angles are congruent. A linear pair of congruent angles. What do you know about these lines? Wait a second. If these two angles are congruent, I could call this x, and then since they're congruent, I could also call this x. Well, what do you know about any two angles in a linear pair? What do you know about these angles marked x and x? If they're on a line together, they should add up to 180 or be supplementary. Actually, linear pair postulate said that two angles on a line add up to 180, dealing with angle addition. So I know that these two angles add up to 180 because they're together on a line. They are a linear pair. Well, x plus x is 2x. And that equals 180, and now I divide by 2 and I find out that x is 90 degrees. And I suppose that makes sense, because these would have to be 90-degree angles so that they are the same measure and add up to 180. Well, let's fill in the blank then. If we have this scenario happening, what do you know about these original lines? If these are 90 degrees, these lines are, keyword today, perpendicular. They have to cross at a right angle. I know I have these 90-degree or right angles there. Okay. This next theorem, if two lines are perpendicular, I'm going to draw that right away. If two lines are perpendicular, what does that mean? They intersect to form a right angle. It says here, then they intersect to form how many right angles? If I know that that one angle there is a right angle, how many right angles do I actually have? Well, wait, don't I know that vertical angles are always congruent, making this a right angle? And don't I know that linear pairs have to add up to 180? So if this is a right angle or 90 degrees, then this would have to be 90 degrees, and all four of these are 90-degree angles or right angles. So if you know two lines are perpendicular and you see only one marked, you know all four are actually right angles. Let's use one of those theorems here in this picture. It says in the figure, angles 1 and 2 are congruent. So 1 is congruent to 2, and I'll put the arcs. So what can you conclude about the measure of angle 2? Well, if these are congruent angles, and they're a linear pair, they're together on a line, they add up to 180, we just discussed that the measure of angle 2 would have to be 90 degrees. So was the measure of angle 1. And if we wanted to give a reason, it would be theorem 3.8 here. It doesn't have a nice title. Theorem 3.8, so I'm just going to write that out. But that said, if you have two congruent angles that are a linear pair, they would have to be right angles or measure 90 degrees. New theorem here. And we're going to prove this theorem below. It says if two sides of two adjacent angles are perpendicular, then the angles are what? Let's decipher this from the picture. Two sides of two adjacent angles. First of all, adjacent means next to, right? So two sides of two angles that are next to each other, which in this picture, angles 3 and 4 are adjacent because they are next to each other. They share this ray. And it says the two sides are perpendicular, meaning these outside sides here are perpendicular. So I'm going to put that right angle mark there. We know that perpendicular means they meet at a right angle. Well, what do you know about these two angles then? Angles 3 and 4, these adjacent angles. Well, wait a second. If we have perpendicular angles making 90 degrees, don't we know that together 3 and 4 would make a 90-degree angle? And what is the term for two angles that together add up to 90 degrees? If you remember, that term is complementary. Complementary angles add up to 90 degrees. Let's prove this theorem. Okay, so in the picture, Notice we were given two sides of two adjacent angles are perpendicular. So that is what we're given, that these two sides, x, y, that ray, or that line, and xz are perpendicular. And I'm trying to prove that 3 and 4 are complementary. Let's do a paragraph proof, actually. So I'm going to start out and say I am given that line xy is perpendicular to line xz. First statement, first reason, as I was given. Well, what did we mark on the diagram because of that? Now you know that the word perpendicular, or that symbol, means that these lines meet at a right angle. So that's what I'm going to state next. The word perpendicular tells me that I have a right angle. Actually, you know what? I'm going to say this means that. I have to be careful when I name this angle. What angle would be a right angle here? It's going to be angle ZXY. I do have to name with 3 letters here. The angle ZXY is a right angle. And how do I know that? That would be my statement. Angle ZXY is a right angle. But that was from the word perpendicular. And anytime you're getting it from the word, it's by the definition of that word. The definition of perpendicular. That's how I know that that's a right angle. Alright, what else do I know here? Well, I know that if I have a right angle, angle ZXY, don't I know that a right angle measures 90 degrees? And angles 3 and 4 together form angle ZXY. Therefore, they must add up to 90 degrees. Alright, so let's say that we know that the measure of angle 3 plus the measure of angle 4 equals the measure of angle ZXY. And how do you know that you can add 2 smaller angles to get a larger? Well, that's angle addition. I'm adding 2 smaller angles to get a larger. Angle addition. And then since the measure of, or since angle ZXY is a right angle, what do I know that it measures? 90 degrees. Oops. I can actually abbreviate. I was going to write out it measures, but I can just say the measure of angle ZXY equals 90 degrees. Oh, and that would be by definition of right angle. Because a right angle does measure 90 degrees. So now I'm looking up here, since I know angle ZXY is a right angle, that's what we said here, and I know that the measure of angle ZXY is 90 degrees, I'm going to plug in 90 degrees here to show that angles 3 and 4 add up to 90, because that is the definition of complementary, and then I can say, yeah, they're complementary. So now the measure of angle 3 plus the measure of angle 4 equals 90 degrees. Again, how do I know that? Because here I had measure of angle ZXY, and I know the measure of angle ZXY is 90. So 3 plus 4, I'm actually going here. Instead of ZXY, I'm putting 90 degrees. And what allows me to put one thing for another when they're equal is substitution. And I can finally state the thing I've been wanting to say all along. Angles 3 and 4 are complementary because they add up to 90 degrees, which is the definition of the word complementary. Finally, angle 3 and angle 4 are complementary. So I had to use some angle addition. I had to get to the point where I was at I used definition of perpendicular. Is that you have a right angle, angle addition, add to 90, substitute in. And get to the point where 3 and 4 add to 90, so they are complementary by definition. I just proved this statement. If two adjacent angles have their sides being perpendicular, then those angles have to be complementary. So good proof for today. Moving on to some more theorems, actually, with perpendicular lines. we have perpendicular transversal theorem. If a transversal is perpendicular to one of two parallel lines, then it is blank to the other. Remember, a transversal crosses two or more other lines. We're saying it's perpendicular to one of two parallel lines. So why don't I create parallel lines? I'll just accident there. I'm going to copy and paste this just so I know it's going to be parallel. And let's see, we have a transversal being perpendicular, so I'm going to make this look perpendicular to one of two parallel lines. Okay, so it's perpendicular to that one. And I'm going to group all this. Or, there we go. And I'm going to copy and paste here. So if this is true, if we have a perpendicular line, oh, you know what? They said that the lines were parallel. We have a transversal. It is perpendicular to one of two parallel lines, then it is what to the other? Now, if these lines are parallel, what do you know? You know corresponding angles are congruent. You know alternate interior angles are congruent. Alternate exterior angles are congruent. You know consecutive interiors are supplementary. Well, I know if this is a right angle and these lines are parallel, it has to be perpendicular to the other. And that's what I'm filling in here. So if you have parallel lines and you have a transversal perpendicular to one, it has to be perpendicular to the other. Alright. And theorem 3.12 is basically just kind of the reverse of that. Lines perpendicular to a transversal. If two lines are perpendicular to the same line, okay, this and this are both perpendicular to that. Two lines are perpendicular to the same line. Look, these two lines are both perpendicular to this line. Then they are what to each other? I'm going to copy and paste that. So if this picture is true, then what can I say? Well, if these lines are both perpendicular to the transversal, now I have corresponding angles being congruent. Or I could say alternate interior angles are congruent. Here and here. I could say alternate exterior angles are congruent because I know these are all 90. And if that's true, what do you know about these two lines that were both perpendicular to that one? They have to be parallel to each other. This is kind of like how all those converse theorems worked with alternate interiors, alternate exteriors, and corresponding angles. We have two scenarios there. Transversal perpendicular to one of two parallels, then it's perpendicular to both. If you have two lines perpendicular to the same line, then those lines are parallel. And we're going to use those for these examples. Determine which lines are parallel and explain. I'm noticing some right angles given. Now, remember that if this is a right angle, we know all four of these are right angles, or if this is a right angle, we know all four of these, etc. Let's see if we can figure this out. Would S and T have to be parallel? And remember, back here, what I need to show that lines are parallel to each other, they would have to have two lines perpendicular to the same line. Are there, I guess these are my two lines. Now, is one of these transversals, either P or Q, having both, being perpendicular to both? If you notice with line P here, I only have one right angle given. But with line Q, check it out. Q is perpendicular to both S and T. Now this one line is perpendicular to both. Look at that. Two lines perpendicular to the same line. These two lines are both perpendicular to Q. Therefore, they are parallel to each other. So this is lines perpendicular to a transversal. So by that theorem, by lines perpendicular to a transversal, I know that S has to be parallel to T, since from line Q it was perpendicular to both S and T. Get rid of those highlights. Let's look at something else. Do we have any reason to believe that T and U are parallel? P is not perpendicular to either. Q is only perpendicular to T, therefore I can't tell. So I don't know about T and U. What about S and U? P is only perpendicular to S. Q is only perpendicular to S. It's not perpendicular to U that we know of. So I don't know anything about S and U. The last pair of lines that might be parallel would be P and Q. Are they? Basically, is there a transversal that's perpendicular to both of them? And actually, if you look, it's not U, T is only perpendicular to Q, but line S is perpendicular to both P and Q. Therefore, P and Q have to be parallel. So it's still by lines perpendicular to a transversal. S is parallel to T, and P would have to be parallel to Q. So using that theorem from the previous page, if you have two lines perpendicular to the same line, those lines are parallel. And in the example below here, is B parallel to A? Is B parallel to A? I'm just highlighting these lines. Are they parallel? Is there any reason to believe that? Well, transversal C is only perpendicular to one of them, but this line D is perpendicular to both A and B. So, again, by lines perpendicular to a transversal, yes. By lines perpendicular to a transversal, I can say that since line D is perpendicular to both A and B had to be parallel. Check it out, these are consecutive interiors. They are supplementary, and so therefore A and B would have to be parallel. And I'm going to mark them now, because now I know this. A has to be parallel to B. Get rid of the highlights here. And then the next question, is B perpendicular to C? This is the only place where there wasn't a right angle marked, like the only set of intersections where we don't know, So the question is, do they have to be perpendicular? Well, now that I know that A and B are parallel from the previous one, and C is a transversal for both of those, I would say, yes, I do. That's the actual first one we had here, perpendicular transversal. If a transversal perpendicular to one of two parallel lines, it is perpendicular to the other. Check it out. We have a transversal perpendicular to one of these two parallel lines, therefore it has to be perpendicular to the other. This was called perpendicular transversal theorem. Perpendicular transversal theorem. So using some of those perpendicular things, talking about parallel lines and transversals. And finally, last thing we're talking about is just distance to a line from a point and distance between parallel lines. Now, anytime you're told to find the distance from a point to a line, you need to look at the length of the perpendicular segment from that point to the line, because this is the shortest distance. It's the quickest distance to get from that point to the line. If I just said, find the distance from point to line, you would not measure here. Okay, because that's not the shortest distance from that point to the line. You wouldn't measure out this way. Not the shortest distance. If you go like this, you're getting a little bit closer. But the best measurement would be along a perpendicular from that point to that line. You need to go at a right angle. That would be the correct distance from that point to that line. You want the shortest distance, so you're going at a perpendicular. Okay? And kind of similar here, the distance between two parallel lines. If these lines are really parallel, you can mark them with arrows. But you want the length of any perpendicular segment joining the line. So we need to go perpendicular to both. Perpendicular here and here with these parallel lines. This would be the distance then between the two lines. You're not going to measure at some random crazy angle. Okay, you have to go to right angle. Again, that would be the shortest distance between those lines. Because if you're not going at a right angle, you could eventually get infinite lengths. Okay, so with distances, always going at a right angle. Looking at some theorems with perpendicular lines today.